Um, yeah, so hey everyone, I'm Josh. I'm a PhD student at MIT.
I'm Lily. I'm an undergrad at MIT.
Yeah, and we wrote this paper for an iClear workshop, which we'll be presenting there, and then we are currently working on a conference length submission of it for NeurIPS. Yeah.
Yeah. So
I'll let Lily take it away.
okay. Yeah. So I'm not sure whether you guys have had the time to read it. Can I? Is this sharing? This?
Yeah, it should be sharing here. Yeah.
Oh, okay.
Yeah.
Yeah. So basically, our project is on investigating the high frequency latents in SAEs. So I know there may be some issues with SAEs, but for now, we're just gonna use them. And so like in the Gemascope SAEs and a bunch of other like GPT-2 SAEs, I think people have observed that there are a set of latents that fire very frequently. So maybe on like more than half the tokens or almost all the tokens, and they seem kind of uninterpretable because most features correspond to like a singular concept or they're supposed to, but since they fire on like maybe like 50% of the text of all text, so that seems like we didn't really know what was going on. And I think in like one of Entopic's work, they said that if you increase the sparsity penalty or something, you can get rid of this high frequency latents. And we thought that we would try and like look into this further, and because we thought that maybe some of these dense like high frequency features are like truly high frequency features, because it seems plausible that a model is tracking a direction in activation space that like maybe occurs on every token. For example, you can imagine like context position if it's keeping track of the context position. So that was like why we started this work. And so in this paper, we just kind of explore the high frequency latents, and it's kind of organized in two parts. The first part is just the geometry and some characteristics that we find are pretty universal of the high frequency latents, and then we also investigate their interpretability. So I think in the first section,
and I guess just a couple other thoughts on this also is that like I think it's pretty interesting to look into this because a lot of kind of just to emphasize that like in Neil's recent post they talk about how one of the things they're trying to do is like remove the high frequency latents, but I think the big takeaway of our work is that actually they seem to be pretty meaningful. Pretty much all of them, or at least a large portion of them, we can like interpret in some way.
Yeah. Yeah. So I guess the first interesting thing that we found about high frequency latents is that they occur in antipodal.
I guess actually, did anyone have questions so far? If not, it's okay. Sorry.
Okay. Yeah. So
feel free to interrupt your questions also.
Yeah, please interrupt. So the geometry of high frequency latents is pretty interesting. So we know that because of like the superposition hypothesis, whatever, that like most SAE features, we expect them to be mostly orthogonal to every other feature. But we find that these high frequency latents actually occur in pairs. So like in terms of their cosine similarity, each one has a pair that is pointing in the opposite direction. And so this means that the SAE learns actually is just one direction, but it needs two features to represent that because of the like top K or like jump ReLU activation. Yeah. So in this,
and if you train with, we don't have it in this paper, but if you train with, if you train with a top K by absolute value, then this goes away.
Yeah.
Right.
So if you allow like activations to be negative, then the pairs go away and you just get like one direction that is frequently occurring. And yeah, so for example, in the high frequency features, let's say we have two that are like maybe like 0.3 or 0.4 frequency, but because they occur in a pair and they never co-occur on the same token, so it's actually kind of a feature that's lighting up or a direction that's being used like 80% of the time. So yes, actually, I guess even more high frequency than we expected. Yeah, and these kind of pairing only occurs among high frequency features, and all the pairs are high frequency features. Yeah, and one other slightly interesting thing that we also found is that the high frequency features are more aligned with the bias, the SAE like bias vector, which we did not have a great explanation for, right?
Yeah, there's also this little spike here that you can basically ignore. These are like the BOS tokens. So the features on the BOS token also align with the bias, but they're like, I guess, less interesting. Yeah, maybe you might kind of think that like one thing that could be happening is the bias is actually, I just thought of this now, is that the bias is learning like the average of those feature directions or something, because they occur so frequently, they're kind of being like absorbed into the bias and like the average of them, and so it's like similar in that sense. Maybe that's a good explanation.
Yeah, that makes sense. Because, like, I mean, later on we say how like a lot of the high frequency features also are like in the top PCA component, so it's just like there's high variance.
Yeah,
during.
yeah, that could be. It could be a result of that.
Yeah. So we had this hypothesis that because these features are so high frequency and a lot of them co-occur, that the SAE might not actually learn the true basis. For example, if you have like two, like in a plane, right, like two directions that occur at the same time, you can learn like any basis that spans the same space. And so what we did was training SAEs with different seeds and finding the high frequency latents, and then we find that like the exact SE like feature directions might not be rediscovered, but the space is very similar between the different seeds.
Yeah, the intuition I guess here just to emphasize is that like maybe there's like some true like dense latents, dense features of the model. Like it has some, as we'll get into exactly what these might be later on. But if these basically always occur, there's no reason for a sparse autoencoder to learn feature latents that like lie along the true features. Any random or orthogonal basis of the dense subspace will have the exact same reconstruction and sparsity penalty.
Yeah.
And so basically what we find here is that like some evidence for this, because even though the SE features that get learned aren't exactly the same, subspaces seem similar across the seeds.
Mm-hmm. And yeah, so I guess to just make sure that these high frequency features are not an artifact of SE training, we ablate this subspace that we found. So like the subspace spanned by the high frequency latents that we train normally, and then now we train a new SAE on the activation, but with that space ablated. And we do indeed find that these features, like these high frequency features, disappear. I think it's in the appendix, right? Yeah, it's kind of hard to see here, but it's the black line, and basically there's no more high frequency features. Yeah.
This is like we go back to that. This is like frequency on the x-axis. So there's like, you can see for all different seeds, it's like the spike over here. Those are like the different sets of high frequency latents in different seeds, and then this black one is with the that like high frequency subspace ablated, and there's like, yeah, you can see that there's a lot less features being learned, and that this right component, high frequency component.
Yeah. Yeah, again, like a lot of high frequency latents lie in the top PCE subspace, but they're not exactly just aligned with the PCA component. So it seems that the SAE is still breaking down something meaningful.
Yeah.
And so I guess these are general characteristics. So I guess to summarize, the most interesting thing would be the antipodal pairing that we find in these high frequency latents. And yeah, so now we try and zoom into them and see if we can interpret them. So I think we focus.
Any questions about the geometry before we go into interpretability stuff? I guess, yeah, just the nice takeaway so far is that like seems like this is a real subspace, not just like a bunch of like artifacts of training, and maybe there's some interesting
there is a question on the chat on the reading group.
Let me open that up. Yeah, how do I? Oh, there we are.
Yeah, I can read it otherwise, but
no, I see it.
Yeah, so in this we mostly focus on layer 12 of Gemma 2b, which is like the middle-ish layer, and we don't show it in this paper, but like now we see that yes, there are high frequency features in every layer, and
yeah, so I think that we're basically in the NURBS version of the paper, we're going to like do a study by layer, and it seems like what we find that mostly like these features are like similar by layer. The frequency features are similar by layer, but the ones at the end there's like more like with the entropy subspace. At the beginning, it might be a little different too.
Yeah, I think it generally seems that at the beginning, these high frequency features occur on like a token or short phrases level, and then in the middle they start occurring in longer chunks and seem to be tracking some feature over like a longer length of the text. And yeah, like a lot of these features are kind of preserved by cosine similarity between layers.
Intuition for they definitely seem more. I think many things middle layers are good for. Middle layers are probably best for steering too. Probing, I think they're best for. Editing, I'm not sure. Doesn't Rome also do mid layers? Rome does early. Okay. Yeah, I don't know. Early to mid. Okay. Yeah. My intuition is that mid is like where the model's like actual like processing is happening. And since Rome is editing facts, maybe that's like a little earlier. And then the actual like high level concepts that are based off those facts get like processed in the mid layers. And then the late layer is doing some like I don't know high level hand wavy stuff. But yeah, I'm think there's like Vedong, Wes and Max had a cool paper on this on like the stages in a transformer. I think hopefully our paper has some interesting insights when we're done with it about like what's different by layers. Yeah. Cool.
Yeah, so I guess moving on to interpretability. So yeah, in this we focus on layer 12. So just by looking at the features, we did run a bunch of experiments. So we found some interesting things. So the first is that there is a context position latent, or at least one of the features tracks context position in like every context. And so it's like it fires a lot and strongly at the beginning of a context, and then it like decreases pretty like gradually throughout. And I guess this is regardless of like what the context is about. So it seems to be tracking context position. I guess like in terms of how it's used, we didn't really look into that, but yeah, we just wanted to show that this feature is tracking something important. Yeah, and then I guess another way we found that features differed is by like their firing like lengths, or like how we call it chunkiness, like how whether they fire in chunks, like long chunks. So like one like within a pair, right? Like does one of them fire for a chunk and then the next one fires, or is it that like they kind of fire like alternatingly or like on a token level? And we find that
we have some plots of that, right? Like some actual examples. Yeah.
Yeah. So for example, like this one, I would consider it a less chunky feature because it's just firing more like words. And if you just look at like the highlights of the words, you can kind of see that
like the red is these are like showing a pair, like the antipodal pair, and the red is one of the pair and the blue is the other.
Yeah. So
and then where's like a more like here's more chunky ones, right?
Yeah.
Like you can see here, like the average like run length is like pretty long here.
And so we hypothesized that the short ones are kind of the non-chunky ones are tracking some kind of like part of speech, or like depends on the type of word. So like maybe like nouns and verbs, there's like connectors, conjunctions, and maybe that it's like maybe the model learns that like after like a conjunction is like more likely to have a noun or something. So it could be useful for it to store this feature. Whereas like for the longer chunk firing ones, so this is what we're actually working on like right now, but it's like you can kind of see that just by eyeballing it, it seemed to us that it's tracking like different, like within a context there's like some meaning variance, right? Because like the context might talk about like, for example, like a study and the results of the study and then the scientific concepts, and it kind of seems that the feature is like tracking this direction along which the meaning varies. Yeah, right now we're trying to do some like steering things to like see if we can steer the model to like So like I guess like for example with like Golden Gate Cloud, right? If you steer the Golden Gate Bridge feature, it just makes it mention Golden Gate in like every context, no matter like what the previous tokens were. But I think in this one, it seems that we're trying to see if we can steer it to like the same direction is used, not to store like specific universal concepts, but just as the like direction of meeting variance. And we're trying to see if steering it, like in this case, for example, the direction corresponds to like the study versus the like scientific like explanation or whatever. And like we're trying to see if that is actually the case, and like steering it would push it towards one or the other.
Kind of maybe like Max likes to talk about a register.
Yeah.
Right? Like in a computer, when you like pull information into a register, the actual information in the register might be different. But it's like kind of like always in like one very close place. The model, like a program might use the value in register one a lot. And similarly, you might pull like the direction that is most meaningful like into the register, and then like whether the register is like on or not tells you like whether like whether the meaning one or meaning two of the context is fired. But I think it's pretty interesting, but we have to look more into that.
Yeah. And then I guess one other feature that we found was a new line feature. So this pair, one of them always activates at the beginning of like a paragraph or like at the topic sentence, and then the next one activates like in the rest of it. So like in here you can tell. And what's also interesting is that if we just like artificially add new lines to like break up the sentences, that doesn't seem to affect the firing patterns that much. So it seems it's not just like triggering on the new line token that like signals a new paragraph, but like it actually kind of knows like, okay, this is like likely the start of the next paragraph.
I mean, if you think about it, it kind of makes sense. If you're trying to predict a new line, you have to kind of be like listening and like thinking like when it'll end. So if you look here, like it's actually firing before the new line. So it's like kind of successfully predicting like, oh, the sentence seems like it's going to end like to the extension of the administration. Like it kind of like realized, oh, the sentence might end here, or like of the playtesting domain period. It's like, oh, like that's the end of the sentence. So trusted digital response was on Discworld, period. It like kind of already predicts the period, which is kind of cool.
Yeah. And so I guess right now in our current work, we find that this new line feature occurs like in the early to mid layers, like throughout, and it's preserved.
I'll go back up to the main body here.
Mm-hmm. So yeah, I guess like here we just show some like slightly more quantitative support for like what we just said. It's like if you plot like the average or like percent of total activation at like each position from the last new line, you can see that one feature strongly activates on like when it's close to the last new line, which is the beginning of the new paragraph feature.
Yeah. One other feature that I guess that we've mentioned is that there's like one that seems to fire on like digits.
Yeah.
Right. So similarly, you can show like the percent of total activation. What is the numbers here again?
Distance to the nearest.
Oh, I see. Yeah. So like this is saying like this like blue feature like fires a lot more like in the when it's like close to a token than like the other high frequency latents. Yeah. So I think our vision here is like to do this for like most of the high frequency latents to prove that they're interpretable. And maybe like a lesson to take away here is that like auto interp is like pretty bad, and if you just like try really hard, then like many things that you thought were uninterpretable actually might be interpretable.
Yeah, because sometimes you have to look at like a context level.
Yeah, or make a lot of graphs or try a lot of hypotheses. Yeah, is there anything else that we?
I mean, not really. Yeah, I guess the lesson is that we claim that high frequency latents likely represent true dense language model features, and that SEs have the sparsity penalty, which is useful for like most of the like dictionary learning and stuff. But maybe like it'll be useful to have a dense channel or some kind of like space where you allow some dense features, because those are actually useful for the model.
Yeah, actually figuring out what these dense latents are seems hard but tractable, I would say. Yeah, I think that's kind of all we got. It's a shortish paper, so I hope that's all right, that the reading group's not going to go too long. But yeah, any other questions?
It's fine. Maybe people have questions. I think I think my main question was about the layer 12 thing too, but you already said you are going to look into other layers.
Yeah.
later.
Yeah, if you're curious, we can tell. Yeah, basically, yeah, we're looking at other layers, exactly.
I mean, there's the other paper in workshop, right, on the last layers.
Yeah, the last layer seems like fundamentally different. Like, so this is from Alessandro, who we're joining with to write the NURBS paper, and they found that the last layer has to do a lot with like the entropy subspace, which is like the lowest 10 dimensions of the unembedding matrix. But it does kind of seem like in other layers it's like similar-ish high frequency things, right?
Yeah.
Yeah. Exactly. Yeah, Alessandro was the one who wrote that conference grounds paper, so I think he's just connecting. Yeah, exactly. Yeah. First layer?
First layer? I think we just see a lot of like very token level things that maybe correspond to like, well, I guess they'll correspond to embeddings or like part of speech. Yeah, but we haven't conclusive.
Yeah. I mean, it definitely makes sense that they should be token level because it's so early. Yeah, do you have there's some basic parts of speech you think are like the early ones?
Probably, yeah.
Yeah, okay. I see people typing, so yeah. We can answer over text too, that's fine. Seeds are just randomizing the initial weights of the SAE, and it actually have a pretty big effect. You can basically, like, there's this paper from a Luther showing that you learn different features of different seeds. Hypothesis for latents come in geometrical opposite pairs because probably they represent one latent that fires a lot, and maybe because it fires so much, the bias kind of learned like an average instead of like, oh, maybe this is it. Maybe the bias learned the average of the high frequency feature instead of learning the origin. And then because it learned the average, it reduces loss because it doesn't always need to fire.
Yeah.
But then you have to be able to go in both directions, both less and more. That's what happened. Okay, that's my hypothesis. So the bias learned I thought it made sense. Yes. So that's why also the bias is fit. So because it occurred so much, the bias learned the average. So it doesn't always need to fire then, which is why we see that in the center it doesn't fire as much as only on the higher things, right? To jump ReLU, and then it's high similarity because now you're like pointing to the middle of this thing, and it's geometrically opposing now because you have to be able to go both directions. Okay, I think that's all I'm saying.
Do you? Wait, but there's other people saying things.
Subspace is just the vector space containing all the decoder directions. That's in the activation space. So like if you have like if you start with if you start with like 10 yeah, so like if you start with the subspace the subspace is just saying like take all the decoder directions and like look at the space that's containing all of them. Lily, do you want to answer Jason's question? Because you started Mech Interp really fast recently.
So fast. I think. Wait, I don't know. I think probably SAEs were a very intuitive kind of thing to start with. I feel like it's because it's like the way I think about it's like mostly like linear algebra and like basis, and yeah. So I think that was a good way to start for me. I also don't pretend like I know too much about the rest of Mech Interp, which I think is like slightly harder. But yeah, I mean, I think SAEs are cool. So, and like a lot of stuff is like open source, right, on like Gemma Scope. So, yeah.
Yeah.
I guess I want to ask about maybe explain it more and it's not appendix and I don't remember it. But about related to the previous thing, for the negative and positive versions of the latents, like how does that look? Or like for example, there is a latent that is about you say it seems to indicate position. How does that look like? Do you think like half of them are negative? And like it's like some sigmoid thing where it indicates position depending on that, or like how does the structure of the activations of the latent look like?
So in this case, when we trained our top K SEs, the context position feature, there's only one. It might not come in a pair. So if it's only one, then we see that the frequency is often like 0.9 or something, and so the activation is just like high or like really low. I think in some of the Gemascope SEs, we do see that the ones that seem to track context position come in pairs. So you just have like one feature that fires at the start very highly and then it goes to 0, and then in the middle it's like kind of 0 for both, and then towards the end of the context you have the other feature starting to fire like stronger and stronger. Yeah.
But in this one, when it's only one, do you find that it goes up and down?
I think yeah. Like so even when it's only one, like the average strength seems to like I think I don't know if we have it in this. Do we have context position here?
I don't think we showed the text example, but
you have one in your doc, but we don't have to share the
Yeah.
whole doc. Basically, yeah, it does seem like the strength decreases in terms of context position.
yeah, like this histogram is kind of hard to see, but it's like on the x-axis is activation strength, and then the yellow ones are like early in context, and then the purple ones are later in context, and then that's the histogram. So for feature 1, which is the context position one, it's like early in context, it's like mostly firing pretty strongly, and then it gets weaker and weaker. Whereas for another high frequency feature, it doesn't have much dependence on context position.
Yeah, this one down here is like just like a baseline, so you can compare, and this one up here shows like this one's like super. Yeah, exactly. Like this, or like early context positions like seem to have mostly higher firings, but even within a context, you'll see like it like starts super high activation and like goes down as the context goes on. Are there other questions here? Let me see.
Yeah, I can unmute for slightly bit. Yeah, I've been in the chat. Sorry, but can I ask if I think I put something in the chat about the basically getting rid of a subspace? Are you seeing subspace as a collection of vectors and just like moving those directions?
Yeah, so I guess we have the vectors, let's say like 5 pairs that span the subspace. And so if we want to like ablate, we can just like take a QR decomposition of that and like project, like let's say like we want to see like how much of a random vector is in the subspace. We can project that onto the subspace using the projection matrix of the subspace, which is created from like it has to be orthogonal. So yeah.
So this is something kind of curious to me about subspaces in general is if you're taking like a bunch of vector, let's like simplify it to like maybe 3D first, right? And let's say you have two vectors, right? In this 3D subspace, right? And then you want to like know out those two vectors. So you project it into the subspace and you get rid of that subspace. And now you're left with like one dimension, right?
Well, you're left with still 3 dimensions, right? Like if you do the projection, so like what you can do is say you have a vector x. You can subtract out and you have a subspace projection matrix 2D like P. You can set x equal to like x minus like x p transposed. And that will like project it down and then project it back up. And then you can basically subtract like this will subtract out not just like the value of the projection, but the actual like vector.
Right. So you still end up with like a vector in 3D, except for 2 of these directions, the value is like 0, I guess.
Exactly.
Okay. That's interesting. Yeah. Thanks.
Let's see. I think there were some other questions in the chat. Let me pull it up. Yeah, I think we answered the question from Unai too about finding the basis, and then we do a QR decomposition and then project it there. Yeah. Cool.
If you don't mind me follow up on the seed question.
Yeah.
So the seed, like different seed, different sparse features, right? And how like how real do you think the features are? Like, are they like are these sparse features very clearly associated with like a concept, or have you like done some manual sort of
just
work?
high frequency ones.
Uh,
Sorry, in general in SAEs or just the high frequency latents?
Yeah, for both. I gather that for the high frequency ones, it's like a more general concept. But yeah, in general as well, that would be interesting.
Yeah, I guess. I mean, it's just like a general SAE question. In general, it seems like concepts seem like vaguely monosemantic, but also maybe not. I don't know if I believe anymore in like ground truth model features. I think that like SAEs are like a useful decomposition of the space. And it's okay if they're not like always the same. And the high frequency latents maybe like there is some like true manifold of like meaning in the model, and like these might be like subspaces instead of like directions.
Right.
But some of them might be directions. Yeah.
Some might be circles.
Some might be circles, yeah. Yeah, anything else, people?
Wait, what? You mentioned circle. Is there a reason you mentioned circle? Or?
Oh, yeah, I just have written a paper before about like circular features. Yeah. Yeah. A while ago, yeah.
I don't know if it's that one, but there was also a spiral thing for modular addition.
Sorry?
There was also a spiral thing for addition in some other paper.
Oh, yeah, the helix. Yeah, that was Subhash's paper.
Yes.
Yeah. Yes, that's true also. So there might be other circular features. A helix is technically a circle plus linear feature. So there you go. Yeah.
Yeah, I guess you probably don't know if any of the high frequency latents might actually have be some feature with some complicated geometry.
Yeah. Unai, you're saying here that something similar could happen, like as in like we think they're uninterpretable, but we try hard and we interpret them. Yeah, I think that's definitely true. You feel the results. I feel like the results in this paper are a good thing for SAEs because it shows that things we thought were uninterpretable actually were interpretable. Yeah, I would agree. Let me send this paper.
I guess at the same time, like it seems like we need some kind of thing that is not just sparsity, because otherwise we're going to miss. And there's also the positive and negative thing. There was also another paper where they did like try to do steering with on the sparse encoder basis, and they also had problems with that. If the model, like, since in the sparse encoder the positive and negative, depending on how you do it, but are going to be like different features. It could be that you want to steer the model to not have some concept, and the negative of that concept doesn't happen on the training data. And then it seems like in some cases we will want something where the fact that the negative of the direction is meaningful comes back in terms of the person encoder having to learn both sides separately, which is, it feels like there is, I don't know, feels like there is some things pointing here to how some better version of sparse encoder might look like. But
Yeah,
don't know
I
how
agree.
to-
I
how
think
that will exactly work.
incentives other than sparsity seem really good. But I don't really know exactly what they would be. Maybe circuit sparsity, but even that I'm not sure.
So I think I'm just talking because I was writing in the chat, so I think that's better if I talk. So I was thinking about this like lately about the MSC problem and so on. So like I was thinking, what if we could like for instance like try to guide the SAE to learn some features that we would like to, right? So for instance, I was like thinking about your paper on sparse on linear probing, right? So what if like if we get images and they provide some kind of condition generation, right? So maybe we could think, what if we create this kind of conditional SAE where we provide the condition to find some like feature, right? So for instance, you have these linear proving datasets that you use in your paper. I think that you use like 100 datasets, different datasets, and so on. Like, what if we concatenate something like the activations of the LLM with like with the condition, right? So you embed the condition or the prompt, whether this is a news headline or whatever, and then we try to predict, to reconstruct the activation, but also to predict whether this was indeed a news headline or not. So something like this would be also probably interesting to.
I think one worry that it might be like less supervised, maybe. But I think if we could figure out a way to make it scalable, it could be cool.
Yes, of course. I mean, the supervision problem is difficult.
But no, I agree. It would be cool. Yeah, there's something similar in that, like, some people like tried to fine tune SAEs for like specific data sets. It's like kind of similar. Yeah, like I think this is like a DeepMind thing. They like fine tune models on like chat specific data, or maybe on like harmfulness data or something. A little similar. Cool. Anything else?
I joined late. I was in another meeting.
No worries. So
Yeah, so that's my question. I just feel embarrassed since you work for the Mech Interp.
Sure.
It's just more what could I do for like what do you guys use for the visualization? Like I'm trying to find like what tool we use for this.
Matplotlib, right?
Wait for the visual.
For the plots.
Yeah.
Yeah.
So if I understand correctly, you just use the Gemma scope and then you which had a pre-trained SCE, which you applied to every layer.
In this case, it was just one layer, but yeah.
Yeah, so you use the Gemma scope, and then you matplotlib it. Oh.
You're talking about this?
Yeah, the red and blue.
Oh,
yeah.
That you.
It's like HTML.
Yeah, just Python generate HTML, right? You can just ask Claude to generate you it's like 20. I mean, you could look at someone else who did this. Like, there's like I think Clément Dumas.
Yeah, because I see a lot of examples doing this, but I just don't know how to do it.
Yeah, so if you just like ask Claude, in Cursor, like, can you visualize like the blue and the red? Like, can you visualize the feature firing blue and red and like display it in like your notebook? Like, it'll work.
And then I guess when I looked at it, Gemma scope looked to be entirely different from transformer lens, like with how, or I use SEE lens, right?
Yeah, so SAE lens lets you access the SAEs, and then transformer lens is used to access like the models that you apply the SAEs to. Yeah, you should be able to combine them.
Okay, I'm just newer to the technical side, so but
Or,
you say you really just ask Claude to visualize the features for each activation in this case.
I mean, you just ask come with code that will visualize the features for you. Like, have a.
I was wondering if there's some library behind the scenes for this.
Like, there is one, so I think they sent one in the chat, like Circuit Viz or something, or whatever.
CV, yeah. I just didn't know how exactly that works.
Yeah. So there are like things you can do, but also it's like 50 lines of code. Like it's not, or like 10 lines of code or something. It's not like a big complicated thing to make these plots.
All right. Okay. I have a basic question here. So maybe it's in the appendix somewhere. So when you're training essays, you subtract the decoder bias from the activation first, and before encoding it, like you have X minus the decoder bias.
Yeah. I think we just used the Luther library.
Okay, and you say that the latents still have high cosine similarity with the bias.
Yeah.
It's the decoder bias.
Yeah.
Okay. Interesting.
I think I in this earlier talk, I think I came with the reason for why this happens, which is that if you have really high frequency latents, then the bias will try to learn the average of those latents so that it doesn't have to fire as much, instead of just learning the order.
Yeah.
And then because you learn the average, you're going to learn two vectors, which is why it's the antipodal thing as well. One going in one direction, one going the other direction from the average, and both of those directions will have a high cosine similarity with the bias.
Ah, so I see. Because you're off by this.
Yeah.
You're in the okay.
That's my hypothesis.
You're saying, but okay. Like, sorry, I got here late.
Yeah, no.
But like high frequency latents have uniquely high similarity with the, like, you're saying multiple of them, or there's just two of them. Like you have a bunch in one direction and a bunch in the opposite direction, or there's two of them.
There's a bunch.
It's like the pairs. It's like you have a pair, and then that pair is orthogonal to like other pairs and other features, but it's just like one pair, like one point this way, one point the other way, and then another one is like mostly orthogonal to this. So like, I guess you can see the cosine similarity. Yeah, like between the pairs, there are different pairs. It's just 0.
Right. So like the high frequency latents have uniquely high. Okay. The experiments lead us to hypothesize that the high frequency latent subspace is not an artifact of SAE training, but represents a subspace of truly dense language model features. So like, all right, like let's say, let's say there's a rank 512 subspace, and it's dense, and it's like uniform, right? Then it doesn't matter which basis you get. You can just have an orthogonal basis of them,
Right.
or you can have like a
Which is one
isotropic basis of latents, and you can rotate them, whatever.
Right. One reason we hypothesize that maybe it would be hard to interpret these latents. Although in practice it seems like they're vaguely aligned with semantic features. It could be because like it's like they occur a lot. They occur like 90% of the time, or 80% of the time, or 70% of the time, but not 100% of the time. And so it's like harder. Like we thought maybe it'll be a little bit skewed, but it would still learn like kind of the monosemantic features, maybe.
Yeah. So like, okay, I feel like there's two possibilities here. Like, one is that it's truly dense, isotropic, right? There's like Gaussian or something like that. There's like nothing to learn here, and so like any like essentially like isotropic solution of like whatever latent active like directions will kind of do the job, right? But maybe this is like, I don't know, maybe it's not enough. Like maybe what is left over, it could be Gaussian, but it's still not like void of content because it's conditional on whatever else activated as well. And so it could just be like, even though there's no special direction per se, it still kind of like refers to like embeddings that don't contain semantic content in themselves, but are like referential to like attention, like induction is here, for example. And so like this is like conditional on like the things that were attended to at the time, and not actually like a unit of semantic content that is consistent between contexts, I guess. So it's like more of a pointer rather than a.
Yeah, we do find not in this paper. We do find like in our like NERS paper there might be some things that are like pointer like things that seem to be like the feature seems to fire on like Lily was saying earlier, like the most like two different meanings of the passage, or like two different types of meaning of the passage. But it does seem like lots of the other features are like pretty like monosemantic, like normal features, like a content position feature and like a new line, like a new line detector and like a digit type of thing. So yeah.
Okay, sorry. That's interesting. I like this.
Thanks.
Is the person next to you the other author?
Yeah, Lily's the first author.
Hello. Oh, I'm not waving. I don't. Can't you see me? Hello. Oh my god, I have a background.
Yeah.
Cool. Maybe I
Cool.
accidentally joined at the end. Yeah.
Oh no, you're good. Yeah, thanks for joining. Do we have any other questions in the thing here? Let me see. Okay. Other SE stuff. Arena. Yes, the HFL subspace, removing the HFL subspace does seem to robustly remove HFLs.
Yeah. Does preserving it? Wouldn't try that.
Yeah, I don't think we tried that. Yeah.
What do you mean by removing the subspace though? Like, what, is the subspace like orthogonal to like all the other stuff?
Yeah,
Like,
so
I would imagine that it's possible to have sparse features that theoretically live in the same space. It's just that it's sparse, right? And like the part that is like high frequency was like before the bias cutoff or something like that, and so the stuff still exists. It's just like not in the sparse feature. I don't know if that makes sense.
Like, yeah, that's possible. But we basically, in the experiment, we just take out the dense subspace. And maybe we're removing some sparse features too. But the main thing is that once you take out this dense subspace, none of the new high frequency features get learned. None of the old high frequency features get learned. So like it's kind of showing that it's not just like an artifact of training. Like you can fix it by here, this plot, yeah. You can fix it by just like removing the high frequency subspace. Like this is the ablated thing here.
The high frequency
like
subspace
without,
is not the full space. It's like smaller.
Spanned by only maybe like 10 or 20 features. So it's
Interesting.
like,
Interesting.
Yeah.
I would not expect that.
Well, you just take the 10 or 20 features that are the high frequency ones, and then you take what that spans.
I suppose.
And that's a lot less than like the 4,000 dimensions of the space overall. Yeah.
Interesting. So is this like a top KSA? Okay, I guess that would help, but what's K in this top K? How many latents are active on any given activation?
64.
A 4?
64.
Oh, 60. Okay. Interesting. Yeah, that's interesting. There's only 20 of them.
Yeah, it depends on the layer and the cutoff.
Yeah, but if you use like the same cutoff and you like increase the width of the SAE or like the K, it doesn't change like linearly with the width of the K or something. So it seems that it's like a true dense thing.
Mm-hmm.
Yeah.
Thanks for presenting.
Yeah. Yeah, so we'll have a paper, like a conference paper on this coming out with, hopefully, for nerves. It's going to happen for nerves. Yeah. Yeah. Anything else? Oh, we got more questions. Oh, thanks. Okay. Good luck. Thanks. Okay, if that's all, we can wrap up a little bit early. Thanks for all the great questions.
Fantastic. Thank you.
Yeah.
Thanks for presenting.
All right.
Thanks for coming.
Bye.
Yes, stop the recording.
Again, Victor. Wasn't here for the previous weeks. I was sick.
Yeah, let me close the recording because right now it's dying. It's
Oh
a,
my god, dude. Publish a paper. Wow. Damn. Is it hard?
Oh yeah, how's the thumbnails made from